From a subtle bounce to a full-screen transition, animations are everywhere in the apps we use daily. But they're not just for aesthetic purposes. They provide critical feedback, guide our actions, and carry unique information essential for understanding the interface. Modern computational approaches, especially vision language models or VLMs, are increasingly capable at UI understanding, but they mostly rely on static screenshots. This misses a major piece of the puzzle. Information encoded in motion, like a shake motion indicating a wrong password, or bouncing dots visualizing the user's voice input is received, is likely to get lost, especially when that meaning cannot be inferred from static graphics or text alone. This led us to our core question: how well do state-of-the-art VLMs actually understand these dynamic UI animations? We systematically evaluate state-of-the-art vision language models to find out. To test this, we built a new dataset of 300 UI animations collected from a wide range of real-world applications. Each animation was carefully annotated with time range, context, and the region of interest. We then had both the UI experts categorize the animation purpose and average users describe animation meaning, giving us a rich ground truth to compare against. Our evaluation was designed to be hierarchical. We started with the basics. Can VLMs even perceive primitive effects like movement or fading? Then, we moved to higher-level categorization. Can they categorize an animation into one of the 7 animation purposes? And crucially, how well do their interpretations align with those of humans? Finally, we investigated the limitations and potential factors for improving their performance. We found that most models were nearly perfect at recognizing basic animation effects. They can reliably tell the difference between a rotation, a size change, a color change, or a morph. But when understanding the purpose, the picture gets more complex. The best-performing model achieved a classification accuracy of 0.643, which is promising, but a clear performance gap still exists. Models performed worse on more subtle categories like aesthetic and highlight. These animations were frequently misclassified or resulted in a lack of consensus among the different VLM predictions, indicating confusion or inconsistent reasoning. Regarding alignment with human understanding, we found that VLM interpretations capture the gist of an animation but often miss key details, achieving an average semantic similarity score of 3.51 out of 5. VLMs were more likely to fail when animations were small or subtle, like the shake animation for an incorrect password. This points to a core limitation, a deficit in fine-grained motion perception. So what can we do to make it better? We experimented by giving the models extra information, including encoding motion into video frames, more contextual information, and textual description of the animation. We found that while encoding motion alone reduces performance, providing all 3 information led to the biggest performance jump, indicating the importance of contextual information and VLM's bottleneck of perception for animation understanding. Our work provides the first systematic evaluation of how well VLMs understand UI animations and introduces a richly annotated dataset to drive future research. While they show promise, VLMs could still benefit from a better way to encode or understand animation motions and interpret them within the context. Improving these capabilities will unlock new applications in accessibility, automated design critique, and even generating more intuitive and effective animations.